All right, so to pick up from last lecture video, I keep saying lecture. I'm so used to I've been saying it for 20 years. For the last video, we talked about the fact that we had come up with this tentative, and as we'll see, incorrect set of conditions. Okay. For constructive interference, we said that 2t had to equal m lambda, where t is the thickness, lambda is the wavelength of the light, right? The laser puts out a light of wavelength lambda. Okay. And m is the index. All right. Because any one of those phase shifts will do. Speaking of phase shifts, I need to correct. We need to make two corrections of this. The first one has to do with phase shifts upon reflection. There are 2 points in this picture where there is a reflection. There's a reflection at A, where the total incident beam reflects back, becomes ray 1. There's a second reflection off the back of the film at point B. There's a reflection back into the film, okay, that becomes ray number 2. But remember from a couple of lectures ago, when light goes from a low index to a high index and reflects off of a medium of higher index, so put it this way, when light reflects off of a medium of higher index, there's a phase shift. When light reflects off of a medium that is of a lower index, there is no phase shift. So at A, there is a lambda over 2 phase shift at A, because we're going from air to soap. Light reflects off the soap. So ray number 1 is shifted relative to the incident ray. It's as if you took it and shifted the whole wave by a half wavelength, like I did a couple videos ago with the red light. Okay, but at point B, we're going from a high index, and then light is reflecting off of a lower index. We're going, right, is reflecting off of this boundary, which goes from a higher to a lower index. So there is no phase shift. Not any at all. In other words, because there is a phase shift at A, but not at B, these conditions need to be flipped. Okay? Before our condition for constructive interference, 2t equals m lambda, that now becomes our condition for destructive interference, because there is a built-in phase shift already. And our condition for destructive interference, 2t m plus 1/2 lambda, becomes our condition for constructive interference. So because there's a single phase shift here, we need to flip the conditions. Okay? This becomes a condition for destructive, the first one, and the second one becomes the condition for constructive. All right? Second thing we need to adjust for is our tentative and wrong conclusion is that the wavelength inside the soap film is what matters here. Okay? The number of wavelengths you can pack inside the soap film is what matters. Not how many wavelengths there are out here, because the path length difference, delta, is inside the soap film. So it matters how many wavelengths we can pack into the path length difference, same as it was for the Young's double slit. Okay, so what matters is not the wavelength out here, but the wavelength in there. And if you remember, the wavelength inside in the medium is the wavelength outside divided by the index of refraction of the soap film, of the medium. So basically, we need to take these conclusions here and replace lambda with lambda, with lambda over n. Because the wavelength that's important for the path length difference is the wavelength of the light in the medium, not outside. So now if we make that substitution, we get 2t equals m times lambda over n for destructive interference. And for constructive interference, we have 2t equals, m plus 1/2 times lambda over n. And normally when these things are quoted, when our conditions are quoted, what we see is both sides multiplied through by n, so our condition becomes 2nt equals m lambda. That's for destructive interference. And that m runs 1, 2, 3, ... And for constructive interference, we have 2nt is m plus 1/2 lambda. In that case, m runs 0, 1, 2, ... Okay. All right. That is the case for this example. All right. So what I'm going to do next time, I'll go and shut this video off, and we'll start a new one. I'm going to do an example using these conditions, and then I'm going to show you another example where we have to, again, flip these conditions. And I'll make it clear why. Okay. I'll give you a hint. It's all about counting the number of phase shifts. It's all about counting. In this case, we had 1 at A and none at B, so we had a total of 1 phase shift. Okay, and we'll do an example, calculation using this very setup right now. Well, not right now. Next video. See you then.